Hello and welcome back. Today we are talking about section 5.4, applying definite integration, distribution of wealth, and average value. The main learning objective we're going to be tackling this time is, in particular, finding the area between two curves. This one learning objective is kind of a big one, so we're gonna start off with the basic principle and then use it to apply in a couple of specific cases. So, area between curves, unsurprisingly, will involve the definite integral, because that's kind of what we've been up to lately. Specifically, if you've got two continuous functions, one is always at least the same height as, if not greater than the other, on some interval, then you can say the area between them is given by take the difference between the two functions and integrate them on the interval that you're concerned with. So, I'm a pretty visual person, so having a visual perspective on this would help me with my sort of first glance at this. So if we draw ourselves as generic a picture as possible, so we've got A's and B's, we give ourselves a couple of functions to work with. So we want one of them to be bigger than the other over the entire interval, so we'll pick a couple to work with. And so let's call this, here's g of x. One from up above is our f of x, because just the way the function is, or way this definition is written, we're supposed to be concerned primarily with the situation in which one of them is always above the other for that interval. And then we've got the left and right sides. So we're not supposed to go any farther left than x equals a, or farther right than x equals b. And then right in here is the area in question. So this is the area of that region gives us a. And if you think about the definite integral in general, then this shouldn't be too crazy of a definition. If you just integrated f of x, you would get all the area underneath the red graph. I'll try to do these in different hash marks so we can kind of keep track of this. So the integral of just f of x by itself would be that entire space, because it would go all the way down to the x-axis. And then on the other hand, if we wanted the area underneath just g of x, that would be this direction. And since g of x is the lower graph, that would start here and go down to the x-axis. Well, okay, so if what you really want is just the area up above, you would take the entire red area, you'd subtract off the black area, and what would be left is blue. And that's exactly what this definite integral is suggesting, because we really could do integral of f minus the integral of g, if you recall those nice rules for the definite integral. Okay, so let's try this out in one case. We won't jump into a word problem yet, but we'll try this. So find the area between the graphs of these two functions. So here's f of x, here's g of x. And I think we're going to need a picture here. So let's depict this region, and I'll kind of label stuff as we go here. So this, let's do f of x first. So the function that's on top in this case is right in this region. This is the only area between these two graphs where it's an actually enclosed region. So sometimes your exercises will specify just find the area between these two graphs. And part of our challenge here is figuring out what region is the appropriate one to study. So the region that it's sort of this Eye of Sauron looking thing here in the middle, this is our f of x function. That was 3 minus x squared. And then the one that's upwards sloping here, the concave up one, is our g of x function. So at least on this little sliver in the middle, f of x is the one that's larger. So recall that to find this area, this region between them, then what we're supposed to be figuring out is a definite integral, and it's going to look like f of x minus g of x in this case, because that's the blue graph is the one that's higher. And then the only thing that's missing would be the limits of integration. That is, what are the low and high values that we work from on our x values. So from the graph, it looks like we're pretty close to -1 and 1, but we can algebraically verify that, and that's a good thing to do just in case. So the endpoints of this region basically occur where these functions, the outputs of these functions are equal. So we're really solving f of x equals g of x. We're snagging those formulas from the first slide of this example, and then doing our normal kind of reorganization stuff. So in this case, we're going to add an x squared over. We're going to take away 1, do our normal properties of equality, divide the 2 out of there. And then the only thing we got to be careful of is that this really is plus or minus. When we square root, we're going to introduce that extra possibility that x could have been negative. But that's actually comforting, because that really does mean exactly x equals -1 and x equals +1 are the two limits. So now we're actually ready to compute that area. We know that we have a value of a. There's the left side of our integral and interval, actually. And there's b, there's the upper limit of integration. And then all we really have to do is dump in the actual formulas for f and g. So those, again, we can snag from that first slide. And we're getting pretty good at stuff like this. Remember that this definite integral we can compute with our antiderivative strategies. So our first step is to find an antiderivative for this stuff inside. But that's pretty easy. Well, not easy, straightforward at least. We're using power rule. So one thing to remember is that this 2 we're treating as 2x to the 0. So maybe I can sort of squash that in there. And so we really do get to use power rule on this, that we get to increase the exponent by 1 and then divide by 1, but that doesn't change 2 at all. And then power rule for here as well. So we go up to a cube, and now we've got a fraction for that coefficient. This notation, again, just a reminder, means that we're evaluating from -1 to 1. So we'll plug in 1 for all of our x's here, and then we'll take away all of the negative ones. This gets maybe a little more confusing when there's multiple x's showing up here, but we plug in 1 for all of them and then plug in -1 again for all of the x's. We could get a decimal approximation, but for fraction purposes, we get 8/3. And this is, we don't really know what the units are here because it wasn't a word problem, but some kind of units squared business, basically. One for you to try out. So you're in charge of finding the area between the graphs of y equals 5 minus x and y equals e to the 0.5x, and we're given a specific interval to work over. So my recommendation is you pause the video here, you take a few moments, you try it out, and then I'll work it out here in just a moment. Okay, so let's assume that we're back at this point and you've given this a shot. So let's say that we're going to try graphing this first, just to give ourselves sort of a visual. So if we take a little space, we're probably pretty good at graphing 5 minus x, since this is just a line. So I'll say we get something like that. It is negative sloped and so on. I'm giving these function names even though they weren't explicitly provided here, but we'll call this guy g of x. This is exponential, so it's going to do something like so. And the main thing for us to figure out is on the interval 3 to 4, who's on top, basically, which one of these functions has a larger output. And I think if we check on this between 3 and 4, the e to the x function actually does have a larger output. So here are left and right boundaries, and then between the top and bottoms of these graphs, that actually does make a closed region for us to figure out. So here's the, well, I'll call it R. Here's our region. And then the area of that region is going to be using the definition of our area between two curves. So we can start off, we've got our A to B business. In this case, just so you know, this g of x thing is the one that's actually coming first. So g of x actually is the function on top here. There's nothing sort of sacred about f and g being in the particular order, just the names of the functions. But it is important that the one that has the larger outputs be on top here. We don't have to do what we did in our previous example where we actually solved to find out these endpoints because they just gave them to us. So we're just using our actual formulas here and the endpoints that were handed. So we're actually ready to do antiderivative stuff. One thing I would caution is we're supposed to subtract all of f of x. I won't do the parentheses business here, but if you subtract 5 and then subtract negative x, that's actually a positive once we get to it. So we can use our antiderivative strategies. We've got how to manage e to the stuff, at least e to the k times x, and then power rule for the rest of this. So our x goes up to an x squared. We divide by that new exponent to get a half, and then we're evaluating this from 3 to 4. I'm gonna, just for the sake of you having to watch all this nonsense, I'll leave this to get plugged in, and then remember we'd plug in 4 for all of our x's, we'd plug in 3 for all of our x's, we'd subtract those and get something right around 4.3147-ish. And if you like celebrating your answers, you can put a boxer on that. So that's all for this first video. We'll come back and we'll look at some applications of this whole process.